What about the impact of repeating percentage falls over a long period of time? We've said all along that what we start with doesn't matter. We can apply this to any amount. So we're going to start here with 1. And I want you to imagine that there is some percentage reduction that happens over and over again. And so after a particular period of time, it will have fallen by a half. After another period of time, it will have fallen to a quarter, and then to an eighth, and then to a 16th, and so on. But you can probably see from the black curve on the graph that we could wait forever before it would get to 0, because it just gets smaller and smaller and smaller. Because we can't measure how long it will take to go to 0, because the answer is always infinitely long, a long time ago, mathematicians and scientists decided that what they'd measure instead was how long it takes at a given rate for a quantity to halve. This is time along the bottom. How long does it take for 1 to halve? It takes this long, the length of the time along the bottom. Then the question becomes, after it's halved, how long does it take for it to halve again? How long does it take for it to halve again? And we measure that. For a quarter to become an eighth, to halve again, and we measure that. That this interval, this period of time, and this period of time, and this period of time, and so on as it goes to a 16th, wherever that happens, somewhere here, and when it goes to a 32nd, wherever that happens, over here, all these periods of time are the same. This and this and this and this and this, they're all equal. And this is such an important quantity that we call it something. We call it the half-life. And you might have heard of it in physics, if you've ever looked at something like how long it takes an atom of uranium to decay completely. The answer is it takes infinitely long, but we can measure its half-life. So the half-life is a measure of how quickly something decays, how long it takes for something to fall from its original value, however much that might be. We're just calling it 1, but it makes no difference, from its original value to half its original value. How long does it take at a given percentage rate of decline for something to fall from 1 to a half, and then from a half to halve again to a quarter, and from quarter to halve again to an eighth, and so on and so on and so on forever. And it turns out that as long as the percentage fall remains the same, this is important, while the rate of decrease remains the same, the half-life it does funny things to your eyes when I use the red, but it doesn't. While the rate of decrease remains the same, the half-life remains the same. And this is really important, and we're going to look at it in the specific context of these reinfection rates for COVID-19. What's suddenly become very topical, the COVID-19 reinfection rates, which I think they're calling R0, but we'll just call it R. So what we want to deal with is the COVID-19 reinfection rate. And the important thing, as I'm sure you can appreciate, is that it needs to be less than 1. But the main point that I want to make is that it needs to be a lot less than 1. Clearly, if, and it is a big if R were just a half, then it would go straight down from 1 to a half in just one interval, one epoch of the disease. And that's highly desirable, but it's very difficult to get to that. So let's instead consider a slightly more realistic, if optimistic figure, which is that it's 0.6. 0.6 represents a decrease of 40%, 40% per epoch, because remember we would have to subtract 40 hundredths from 1 to get to our 60 hundredths, or 0.6. In that case, the half-life at 0.6 is 1.35 epochs. In other words, if you treat the length of period during which someone has the disease, is ill, is infectious, so let's say 7 days, it might be 14 days, it varies from person to person. The half-life is about 1.35. And when we look at the red line that I'm drawing at the moment, which is the 0.7 line, and we find that this value, when we come down here, now closer to 2 epochs. In other words, whereas at 0.6 it takes about 1 1/3 episodes of the disease to halve, at 0.7 it takes about 2. Let's put these numbers up here. If we go to R is 0.8, it gets longer again. Disproportionately longer. So that now the half-life is round about 3. What about the upper limit when we have R as about 9, 0.9? Stretches out right up here. This figure here is at something like 6, in fact longer, 6.5 epochs. So if we have an R rate of 0.9, the disease will be around for about 5 times as long as it will be with an R rate of 0.6. So it's clearly not enough. It's important to get it below 1, but it's not enough to get it below 1. Unless we can get the disease down to about an R rate of 0.5 and not much more, it will be around for far too long. At 0.6, the half-life A is about 1.357. At 0.7, which is B, the half-life is 1.943. At 0.8, C, it's just above 3. And then at 0.9, at D, you can see that it does suddenly leap up to over 6, 6.5. That the 0.9 figure is 5 times as big, approximately, as the 0.6 figure, which is why we need to get this number down. If we consider the half-life, what we mean is that when we take 1 to start with, if we wait a length of time for it to halve in size, in other words, for it to go from however big it is, to go from 1 to a half, and then to go from a half to a quarter, and then to go from a quarter to an eighth. A bit rough and ready this. and then for it to go from an eighth to a 16th. And the idea is that the width of these blocks remains the same. So the half-life remains constant while the rate of decrease remains the same.